Hi, my name is Markus Lid. I'm from the Norwegian University of Science and Technology. I'm glad to present to you here today at the second European Conference on Structural Integrity of Additively Manufactured Materials. Today, I will be presenting our work on a finish pass strategy that improves the sidewall angle and the processing time of focused ion beam milled structures. Together with me in this work, I've got Abdullah Ben Afif, Jan Torgersen, and Fritz Prince. And I thought I'd just include a video of me here on this title slide so you can see my face and see my smile. For the rest of this presentation, I'll take away the video and you'll just hear my voice. Okay, so let's start. First, just a really quick intro to what is focused ion beam, or FIB, for those of you who don't know. It usually comes in such a dual beam setup with the SEM, scanning electron microscope, and the focused ion beam. And it would look something more like this. This is the FEI, Thermoscientific Helios G4 instrument. The ions usually come from a liquid metal ion source, typically gallium ions, which are accelerated to anything from 1 to 30 kilovolts. When the ions are hitting the sample, they will have high enough energy that they can break away atoms from the target. This sputtering process is referred to as FIB milling, which is what I will talk about more. FIB milling can be used to create cross-sections, live edit of electronic circuits, and create micro and nanostructures, microfluidic channels, and much more. Probably the most well-known use case is for making lamellas for transition electron microscopes, and this is an area where the FIB is really great because you're able to make these thin sections, even of composite structures, of materials with vastly different material properties. And this is made possible thanks to this cleaning cross-section technique, where you're scanning line by line, closer and closer to the finished surface you want. And this cleaning cross-section method has inspired some of the processes that we're going to explain further in this work. So here in this spaghetti chart, I'm trying to highlight how various different milling settings will have an impact on several different outcomes at once. I just want to highlight specifically the beam current and how it has a nearly linear relation to the sputtering rate, thus the processing time, while there's also an exponential relation to the beam current, and thus the milling detailing quality, just showing that there's a trade-off in the selection of the settings. So FIB systems, they will have a built-in patterning capability, which are quite high level. Say if you want to make some rectangle or circle, it will be some really nice features for patterning these structures. But if you have a bit more complicated structure, say in this ice cream cone, it has more complicated features, and this would better be patterned with a contour offsets. And this is possible with a lower level approach with a Python scripting using something called the FIBMA toolbox, which is created by Victor Deinhardt et al. With this, it's possible to define custom scanning lines and rasterization along these lines. And you can define specific scanning algorithms and scanning processes, and then export these patterning files with a list of dwell points and their coordinates, and dwell times. And so this is what we have done in our patterning approach, which I'll explain next. In this work, we want to present the multi-step patterning strategy, where we are dividing the milling process into the bulk milling and the finish pass, into one or more finish passes. Now, the bulk milling would equivalent to the typical, to the standard milling process, where you have a pattern which is repeated over and over and over again, as you can see here. This would be repeated typically hundreds to thousands of times. Then the next step would be the finish pass, where you could have a small overlap in case you have some angle to the sidewall. And there would be a longer dwell time, and you'd be scanning line by line progressively to the final surface. To test our multi-step patterning approach, we're doing this experiment where we're doing our patterning on a silicon wafer with platinum and aluminum layers, thin layers on top. This is just to have a good imaging contrast in the end. And we designed this test geometry, which has a few different features. It has these trenches of different width, which will make some cross-section of in the end. And it has some positive and negative curvatures. We also made 3 different milling sites. The first one, which is only bulk milling, this will be the reference, as this is more of the typical patterning. And then 2, which has the finish pass, where the last one we're having different beam currents. All this is patterned on the FEI Helios G4 instrument we have here at Nanolab at NTNU. The milling parameters used for this experiment all have an acceleration voltage of 30 kilovolts, which is the highest we can use with this FIB, and a constant pattern flux of 5 nanocoulomb per square micrometer. This would be the setting to change if you want a deeper or less deep pattern. And in this table you can see the settings used. Take note of the constant beam current used for pattern for site A1 and A2, while A3 has multiple different beam conditions, starting with a higher beam current, which will give a higher milling rate, and ending with a lower beam current, giving a finer detail. And take note that to mill this last pattern, we need to do an alignment, because the different beam conditions will not necessarily be perfectly aligned. Just for clarity, I made this visualization so you can see what these patterns actually look like. First, we have this bulk milling, which is starting in the center and moving gradually towards the end. It's using a short dwell time for each coordinate, and this pattern which you're seeing now is repeated thousands of times. Then the next would be the finish pass, where each coordinate has a longer dwell time, and the scan line is progressing step by step towards the finishing edge, and this pattern is only repeated once. Yeah. And here is the result of our experiments. The 3 different columns show images from the 3 different milling sites, where the A1 was just bulk milling and the 2 others have the finish pass. And looking at this second row, we can see how the features around the corners they are getting sharper and sharper, more defined. And then in this last row, we also see the cross-section, which is filled with platinum before cross-sectioned. We see these sidewalls are getting, the slope is gradually changing and becoming straighter. Please also take a note of this feature here in this corner. This is the mark which was patterned beforehand and used for alignment, since we had a different beam conditions than before doing the next pattern. Before starting the milling, we aligned ourselves to this mark to make sure that each pattern came in the right position. As we could see from the last slide, the slopes were changing, and that's visualized in this plot where we made the measurements of the sidewall angles for the different trenches. So here are the different trench widths, and the first, with just the bulk milling, has the highest angle, while the second and third sample, they have significantly steeper sidewalls. Also looking at this other chart, which is showing the milling time, it shows how sample A1 and A2 have nearly the same processing time, which is expected because they're using the same beam current. It's just this small increase in time due to the small overlap of the patterns. A3 is actually showing a lower processing time. That's due to the high beam current used in the first step. Probably this could be significantly improve the processing time by changing the width of the last step, because we can see that the last step took a lot of time. So there's probably quite a bit of room for improving and getting the optimum processing time and still getting a good sidewall angle. To summarize the results of our experiments, we've seen a significant improvement of sidewall angle using this multi-step approach. And there's reduced milling time when using multiple different beam currents that utilize the effect of rapid milling with a high current and finer detail for a low beam current. Further, we would like to study some other aspects with this patterning approach. First of all, we'd like to improve and automate the selection of patterning parameters through various optimization techniques. We can also take into account and change the acceleration voltage on the finished pass to improve the surface quality of the finished surface, just like we talked about with the TEM lamellas. Finally, I want to thank my supervisors, Jan Torgersen at NTNU and Fritz Prince at Stanford University, and all my collaborators there. I also want to acknowledge the Research Council of Norway for supporting Nanolab and the great facilities we have there for fibbing. And especially thanks to everyone who listened to this talk. Please Please reach out if you have any questions, and I'll be happy to hear from you.